This lecture is going to be on the Earth's atmosphere. We're going to be looking at the composition and the characteristics of the atmosphere in a couple different ways. So we're going to be using terms like troposphere, stratosphere. We'll talk about the composition of the atmosphere and some changing conditions. So here goes. The thermal structure of our atmosphere is kind of best identified in this graph, or in this picture here, this illustration, that our lives are mostly lived entirely in the troposphere. The temperature decreases. If I look at what's happening with my temperature, as I increase in elevation, I'm decreasing in temperature, right? Here's my temperature here. And as I rise vertically, it's getting cooler. The stratosphere, or the next layer of atmosphere above the troposphere, the stratosphere is where we find our ozone layer, or oxygen, O3. The ozone layer is a protective shield of shields us from ultraviolet light that damages cells on Earth's surface. So observe the warming trend. The warming trend in the ozone layer is kind of most notable here. So notice that in our troposphere, the graph is moving this way. It's getting cooler. But above the ozone, it's actually warming up, kind of in through the stratosphere, or in through the ozone and then above it. So the warming trend is the result of ultraviolet light, this is a form of energy, being absorbed and re-radiated upward to the air above the ozone. So as a result, the temperatures above the ozone actually increase. So incoming solar radiation, the dangerous UV light, is absorbed by the ozone, and then it re-emits back as heat energy above it. So here we look at the Earth's atmosphere that is dominated by non-reactive nitrogen, about 78% nitrogen. And then it's about, and it's non-reactive due to the triple bond. Nitrogen triple bonds it with itself. But the second most common substance is oxygen, and it's about 21% oxygen. And this is what is required for respiration, for life as we know it. And then there's argon at about 0.9%. And then the rest is a scattering of gases ranging from carbon dioxide, neon, helium, methane, krypton, and hydrogen. So all these others, well, here's carbon dioxide. It kind of made the list into the pie chart. And then here's all the other tiny amounts of gases as well. So our atmosphere is really kind of this heterogeneous mixture of all kinds of different stuff. But the Earth's atmosphere has not been constant in its chemistry and composition. It has changed over the course of geologic time. It is apparent from the idea, if you think about Gaia, that photosynthetic organisms modified the atmosphere to its current composition of 21%. And these very organisms have helped regulate that 21% oxygenated level. So if I go back through time, and I go back to about 4.6, 4.5 billion years ago, the first living cells are found in fossils about 3.5 to about 3.8 billion years ago. But notice, photosynthesis didn't even begin until about 3 billion years ago. And then it was this slow, gradual increase. And we don't even really begin to see or notice a difference in our oxygen levels until about 1.5 billion years ago. And then it starts to increase. And then finally plants begin to dominate or take over. Plants can be photosynthetic organisms. And then they start taking over. And then all of a sudden we have this Cambrian explosion where plants and terrestrial, or anything that is photosynthetic on land, all of a sudden we see this dramatic increase. And if we look here, the graph is very, very specific to saying that our atmospheric oxygen levels have increased in the last, or most recent, 1.5 billion years, and have really exploded in the last about 500 million or 500 million years. But most photosynthetic organisms are oceanic phytoplankton, symbiotic algae and bacteria, right? They're working together. These are the organisms responsible for oxygenating our atmosphere. So this is what's called, in geologic terms, the oxygen of evolution. And in this case, I always call it the oxygen revolution. That the Earth's atmosphere has had a topsy-turvy history of oxygenated atmosphere. That it's fluctuated, and such fluctuations have coincided with mass extinctions on Earth. Photosynthesis is the chemical reaction between sunlight and carbon dioxide that synthesizes into sugars and oxygen gas. So if I look at this, our current levels is noted by 21% at this dashed line. Notice that in the most recent Phanerozoic eon, right, the past 550, 560 million years, we can actually see these fluctuations where oxygen levels were lower than 21%. And all of a sudden, at times, they would peak over it slightly, even up to 25%. And then you see this dip again, and then you see it rise way up here at this location during the Permian, which is a part of the Paleozoic, and this here would be an era. But notice it's been kind of, I use the word topsy-turvy, and I like that word, that even more recently it has kind of stabilized. But historically speaking, in the last 500 million plus or minus years, it's definitely fluctuated above and below the modern day 21%. So let's look at what photosynthesis actually is. It's actually a form of organic biochemistry. That photosynthesis is not exactly as simple as explained from what I said before. Sunlight, water, and carbon dioxide creating these sugars and water. That there are the enzymes and coenzymes that alter the reaction rate. So it's a little bit more complex than that. And I can look at this when I look at this as a molecular and an energy diagram. But you definitely need sunlight, you definitely need water, and you definitely need carbon dioxide. But the process gets a little bit messier. But we do have carbon dioxide and water going in. If I have these in the presence of light, along with these enzymes, I can create these C6H12O6. These are glucose, and this is actually how I form plant matter. And then I also get oxygen and water as well. So it's a little bit more complex. I just want to make sure we refer to that, make sure we understand that. It is more complex. That geologic time here. So let's move into geologic time. That I have these eons. The eons are the big chunks of time. Most of Earth, about 88% of all Earth, is pre-Cambrian. And that only the Phanerozoic is only the most recent 12% of all geologic time. And then we subdivide into eras. And these eras are Paleozoic, Mesozoic, and we are currently in the Cenozoic era. The periods, these are breakdowns as to what was going on during eras based on fossil records. So we further break down eras into periods, and here we are currently in the Quaternary period. And then epochs are further breakdowns of periods. They're more recent time frames in this case. So when we look at the geologic time scale, I think it's important that we start looking at what is taking place. We can start with what's recent, right up here, the recent timeline. Or we can go back and start looking at what was taking place in deep time. And then we kind of go through here from oldest to more recent, or from recent to oldest. And I just want to make sure we look here. Earliest fossil recorded of life is around 3.5, 3.8 billion years ago. We have shelled animals, we have plants, we have amphibians into reptiles, first dinosaurs, we have Pangea, and we'll be talking about a lot of these geologic topics here. Dinosaurs went extinct 66, 65 million years ago. Ice Age begins 1.6 million years ago, and then it ended 10,000 years ago. So a lot of what we're looking at here when we talk climate involves the directness of sunlight. This is what's key to the Earth seasons. This is a result of the axial tilt, but really it comes down to the directness of sunlight. That the directness of sunlight is what's driving the heat energy. That in the winter, right, in the wintertime, we have shorter days with sunlight at very low angles. And we can see that in this picture here. Whereas in the summer, we have a higher, greater sunlight angle, and we have longer days. So we have more sunlight, more heat energy for a longer period of hours. And that's further illustrated here. Direct sunlight, if it's 90 degrees above overhead, this would be at 45 degrees, and this would be at 30 degrees. And we can actually see how we get the insolation at angles near 90 degrees delivers the great amount of power per unit area. So the more direct the sunlight, the more heat energy that we find. And this just kind of reflects that. But let's make sure we go over it one more time. At 40 degree north latitude, that's what these pictures are taken from, we can view the sun's perceived path or arc through the sky. During the summer solstice on June 21st, the angle is not 90 degrees because we are not located at the Tropic of Cancer. We are not located at 23.5 degree north latitude. This picture is located 4 degrees north. So that is 16.5 degrees further north than the Tropic of Cancer. So we have to subtract 16.5 degrees from 90 degrees, and we get 73.5 degrees. And for this picture, that's what this is reflecting. But think of it this way. Chicago is 2 degrees further north than this location, right? We are at 42 degrees north. So our zenith is 71.5 degrees above the horizon. And that should make sense to you. So now we're going to look at what's taking place. We call this the fate of incoming solar radiation. If I have 100% of solar radiation, and we can talk about this in terms of the heat budget, about half of it gets absorbed into land and water right away. But of the rest that isn't, right? So there's other that comes in, right? It's not all of it, but about half of it gets absorbed. We can say that 5% gets scattered back into space. Here we have, and this is just from the atmosphere itself, we could say 20% gets reflected from clouds. And then here we can also say that about 20% is absorbed by the atmosphere. So we're looking at a couple different terms. So we're talking about reflection. That's the process where light bounces back from an object at the same angle at which it encounters a surface with the same intensity. So something that's reflecting off, we think of a mirror. But a lot of materials have a different way in which they reflect light off them. And then there's scattering. This is what produces a larger number of weaker rays that travel in different directions. Our sky is blue as a result of scattering. Blue is preferentially scattered the most and absorbed by the atmosphere last. So we view it as blue. So here's what we call albedo, that different surfaces, light and dark, influence how much heat energy is reflected and or absorbed. That albedo is a measure of an object's reflection of the sun's radiation. In astronomy, many planetary bodies in the solar system are visible due to the reflection of the sun's light off their surfaces, which is why we can see Venus, Mars, and Jupiter. So the measure of albedo is a subjective scale ranging from 0 for completely dark to 1 for completely bright, or meaning it reflects the light altogether. So fresh snow can have an albedo of about 0.9, whereas 90% of the snow is reflected. And coal has an albedo of about 0.1. So when I look at coal, that's not on here, I would say that about 10% of the light is reflected. The Earth has a varying albedo score. On average, the Earth's albedo is around 30%. Some objects have lower albedo scores than expected. The Moon, for example, has a surprisingly low albedo of only 0.12. And there's a picture here, or 12% of the light is reflected from it. So now we've come to the greenhouse effect. We continue to talk about light. That the greenhouse effect describes how sunlight is let into our atmosphere and gases trap and hold on to enough heat to allow for liquid water, or for water H2O to be found in a solid, liquid, and a gaseous state. Liquid water is a critical component that allows for life to evolve on Earth. Water, a liquid medium, provides the perfect medium for complex chemical reactions to take place in single and multicellular organisms. So when looking for life in the cosmos, we look for water, and then we look for life. So let's do this. Let's talk about the greenhouse effect. We have these layers of gases. Sunlight enters, and some of it is absorbed, some of it gets scattered, some of it gets reflected. But much of that heat gets trapped, and that trapping of the heat is actually a very good thing. It's a very healthy thing. It allows for conditions and temperatures to provide for liquid water on the Earth's surface, and that's a good thing for life. And this is where we came to recently, water on Mars. That we have these pictures of Mars, and we have these features of showing that not only was there past water, there's actually currently water in these particular lineae. So if I look at this video here, you would see that these alternating seasons, we have these very cool features, and it's believed to be liquid water on the Earth's surface, on the lunar or the Martian surface. And that's pretty cool to think that there's not only was water, but there actually could be water, and therefore maybe perhaps there could be some beginnings of life or living organisms. So last but not least, I think I'm getting close to the end here. Mechanisms of heat transfer. You've probably learned about conduction, convection, and radiation in the past. But let's look at what conduction is. Conduction is the transfer of heat energy through direct contact, where energy is transferred through the collisions from one molecule to another, with heat flowing from higher temperature to the lower temperature. Whereas convection, where we often think of convection currents, is the transfer of heat by mass movement or circulation within a substance. Convection takes place in fluids, liquids in the oceans, and gases like air. Remember, gases behave like fluids, where atoms and molecules are free to move about. And lastly, there's radiation. Radiation is energy that travels out in all directions from its source. Unlike conduction and convection, which need a medium to travel through, radiant energy readily travels through the vacuum of space. And all three of these take place in the Earth's atmosphere simultaneously.